So you're good to go.
All right. Thank you for joining to listen to this session related to industry safety levels versus aerospace use cases. This discussion has come up, I think, in a few different forums over the last year when some of the working groups were looking at how to compare different products spread across different industries. And I'm taking more of a maybe civil aerospace set of steps since I'm a little bit narrowed in on the aerospace side, you'll see in a minute. But I think it opens a conversation for possible industry papers on this sort of topic, as well as further presentations for people that maybe are coming from other angles. So at any point today, do put questions in the chat. I'm happy to clarify and drive into some topics deeper. So with that, Matt Weber, I'm an associate tech fellow at the Boeing company. I've been with Boeing about 2 years this week. And prior to that, I worked for Rockwell Collins or Collins Aerospace. And I built a lot of DO 178 level D products, so like information management products. And I helped de-risk higher safety criticality products like technology maturation like activities. I have about 17 years in the Linux space, way back to the original like RT preempt stuff. I was doing that in like military radios, mission critical type problem space. So, which is still working today. So if anyone says that like 2.6 kernels aren't operationally viable, they're still there, I'm sure, somewhere. But that sort of progression is sort of where I look at this new problem space of safety in Linux. Real time, it took quite a long time to evolve into something today that I think a lot of people would take for granted when they look at product development. So I come from a little bit of that background, embedded background, Linux and a bunch of different regulated spaces. And to put a little bit of a clause on this, since I did not do level A products, take what's said in here with that grain of salt that it's not guidance for certain. So the Aerospace Working Group within ELISA, we have the charter to develop use cases to inform and influence Linux architecture and tools. And hopefully what you'll see in the slides that follow are some things that touch on the points in this statement about how you tie some maybe the practice and policies, do some practical examples that I'll demonstrate towards the end, and try to just give us a foothold because it's a very large problem space and maybe we make some aspects a little more tangible once we're done going through this today. So the agenda roughly is I'm going to start off with your civil aviation aircraft level development perspective and walk through some of the different standards that are in the safety side, hardware and software, systems safety, hardware, software. Then I'm going to focus purely in on the 178 software aspect, look at the different activities that sort of a life cycle involves, and then we'll look at a very unofficial comparison of sort of like a failure rate view of how different standards and industries have looked at hazard and see if we can get a comparison. I think that's an area where if others have perspective, that would be really interesting to bring to our working groups and events like this in the future. And then use case and demos, I'll go through sort of what the working group has developed and how we're starting to chip away at some of the concept space. So starting out with life cycle. So full life cycle. I'm building a system that's going to be deployed, and has a what we call high criticality. If you're curious about more background of this, the QR code and links at the top will bring you to a lot more information, but I will start at the top. And this is where every development starts. And that is looking at the recommended practices, the ARPs, and progressing through a what is the intended function of a system, what is the assurance that's going to be needed based on what you're trying to mitigate for like failure and hazard and the severity of those. So it's this cycle of assessment and definition. And what that's going to give you is what's called your design assurance levels. So DAL is like a system level definition. The alphabet after it, A, B, C, D, is going to be common with things below your system process, but they may have a slightly different name. So your system process is going to identify things that are safety relevant, and the way those are conveyed downward would be through allocation of functions and requirements to your different domains. So your hardware development and your software development. Hardware and software have two different DO standards that govern them, and they would apply to your A through D um, activities and objectives that I'll share on the next slide. So, so very traditional, define the system, derive the requirements, break the requirements down, flow them with safety intent, as well as security relevant is becoming a flag too that really now comes into play, as there is sort of a system level activity that does a very similar thing to this model for security. And the one key thing that I think how I look at aviation development versus really any other safety practice is these items here on the side in these sections of DO 178C. If you have components that have a specific level assigned, you have to make sure that they are independent time and space, like robust time and space, such that they can't conflict with things at other levels. And that's where some other things like it's called integrated modular architecture, IMA. There's standards around how do you do a mixed set of levels. If you can't accommodate mixed set of levels because of how you've architected it, you have to elevate all components to the most severe level. So if you think about an empty system running no software, and I'm assembling that system up to an operational state, most likely everything related to you getting to that operational state, there's a good amount of probably level A content depending on what your system's, system analysis has flown down. So so that's really key is I can't coexist with different things. So if I think of like Linux deployed on a system, I would probably run Linux fully at a certain level and do the respective activities for it at that level. So, and I think I've only really seen that done level D and below. So nothing above level Delta, to my knowledge, has ever been done with Linux. And you'll see why here on the next slide. So narrowing just in on software. On the left there, you'll see you have the different levels. Then you have the severity of those, and comparison to like the ASIL levels, they're opposite. So your impact is going to be more impactful as you go to level A, versus in ASIL it's to level D. And also the example impact, when you look at the actual failure rate data, it makes a little more sense of where some of these come in. Is like level A is basically you lose a whole aircraft, a lot of people. These systems are that critical to the safety of a very large set of systems. And if you look at example systems for that, it could be like your flight control system, different automated systems. Like say you're flying in a condition where you have no visibility, your terrain awareness is very important, and possibly some automation that does some things to help the pilots. So that's like the super severe case, level A. Level B, a little less severe. Most likely you don't lose the whole aircraft. Your human life impact is a lot less. And you'll hear me cue on the human life aspect a few times. That's one of the interesting things when you compare the standards it's like the magnitude of either reliability and importance because of a massive amount of energy and cost investment, or the scale of souls on board. And this standard is definitely keyed on souls on board. So for level B, it gets a little interesting between A and B because depending on how you do your system analysis, A and B between legacy systems and new systems, things may trend a little differently depending on the functions that are allocated. So like one of the examples here of a flight management system, depending on what you lump into FMS, you may become a level A on a newer airplane. Or depending on like for ECAS, for the engine alerting, depending on if there's any automation beyond just lighting, maybe that bumps it up. So you definitely on every new aircraft, they go through that full system assessment to understand how the software side levels play out.
Nice.
Level
Question.
C, what was that?
I we have two questions.
Sure.
Like why is fuel monitoring, which potentially, I mean, if you don't have fuel anymore, so if you do wrong monitoring, is it something that you say it's just because I basically know how much fuel I've consumed and see how much I have, so that's just a C and not a B. And the other is like
There,
Wi-Fi, a minor, like an
there's,
inconvenient thing, but entertainment
yeah,
is no. Say Wi-Fi should be the same like entertainment.
fair. So for the example, the fuel monitoring, part of your activities of managing your fuel and weight in order to be able to take off would involve systems that are most likely level B. Your level C there is maybe you lose the ability to measure your fuel burn and it causes you to maybe land earlier. Or like also for level C, if your data links go out, it might result in you having to divert to a different airport because maybe you were doing a oceanic route, right? And be too risky to do that jump without having your comms all fully functional. So it's C is more like those systems where it's an aid, but it won't. You can manage when it fails. This may be a way to say it. um, and it's checks and balances in how you're doing your planning pre-flight as well as when you're in flight, and then where other systems may be compensating. Um, level D, the inconvenience one for level D, it's more about I have a system and it needs a definition within the aircraft system of systems. So it needs to be connected to things in ways where data flows need to be recognized, upgradability aspects need to be recognized. Like there's a minor maybe reliability risk to it. It's not like direct safety impact. So that's why like lighting, maintenance systems, maintenance information, connectivity, you need a definition of those because they're going to be installed and provide a certain feature on the plane. But if they fail, it's less of an issue to like reset power to them in flight. And if they don't recover, you probably send a message and say, "Hey, is tech available at the next airport? This needs to be fixed or scheduled for repair." Level E items is a little bit of the Wild West where they might not be part of the airplane configuration directly, and upgradability of those may be more likely like OTA like style. That's why it may be like an airline that owns the plane has operation scenarios where they retrofit stuff into the plane after the fact that maybe is level E, and it really doesn't have to be taken into the overall airplane cert. I don't know. It's subjective based on the hazard and different scenarios, as you can probably tell from how I'm describing it. But actually, that's a really good intro to the next slide here. So when you look at the actual safety levels versus what you're doing for cert, level E doesn't have any of this. So if you're okay with a system being in a plane, it better not have any safety impact because it's not being considered through the actual process formally. So a level D product here at least has requirements, high level, goes through test cases, procedures, results. And, there's a plan for certification written, and you're going to go through activities, and you're tracing a minimal amount of items. Your items here with the purple lines is really, that's where you're getting the higher levels of towards A, where you're adding lower level description, linking to code, and doing more what I would call full life cycle content. So that definitely plays into, definition and rigor and product would move you in the scale. And how you would get to the different levels is sort of what I have here on the right is Appendix A of 178 outlines what we call objectives, activities, and outputs. So here you have the step one, an objective of basically plan, right? We talked about in the document then, here's what that means. Here's the mapping to a respective level. And then here are your outputs, like I need a plan for cert. I need a plan for software development, verification, configuration management, quality. And then for each of these output documents, it talks about, well, to sort of like what longevity and maturity. So it's like config and change management aspects is what the CC category is. So this is done for a whole series of objectives throughout the full life cycle. And the matrices here show, allocation and then respective activity. And if you want more info on that, Steve Vanderleest did a really good overview of this in the QR code, a seminar talk up here in the upper right. And that talk also goes into a little bit conversation on the coverage aspects, how that plays in here. So this one is where it gets a little fun, coming from an aviation side. When I look at it from like an automotive perspective, automotive doesn't really have a level A. And I can understand why in some cases that it's more of a two-dimensional problem, possibly, depending on how you look at it. In the level A case, there's things that just fundamentally can't fail, and then you add redundancy to make that can't fail even more unlikely. And if you look at the failure rates, your level A is the -9th, and your IEC standard does, like a SIL 4 falls into the -9th case, as well as if you look at the military and NASA class levels, the LOR and class both map also to this level. So at the high end, that's interesting analysis sort of, and where I see maybe opportunity in industry is if you look at, if we solve a really sound reference architecture for level A that can support mixed levels of everything else, it actually solves a lot of problems, I think, across a few different industry cases. So interesting. The other one on the opposite end, if we look at what would be like the quality management or what I call like the DAL-E, is definitely unregulated on the aviation side. Things are usually pushed. If you have a company that follows any basic ISO standards, you more than likely will be doing more of a DAL-D for your level E products because you want the basics of requirements and tests and basic quality in what you're doing. So I think a lot of people hug this line, but you're going to see Linux in massive stacks. So like your AI and your graphics stacks are going to hit 100% in your DAL-E first. Your DAL-D can manageably cert those, but you're going to start to see the intended function being systems really stripped down. But until you get to DAL-C, you don't have to do massive coverage and test. So really this line between C and D is huge. because it's holistic, right? Empty system has to be certed to this level holistically, or you have to segregate everything so that they're all isolated. So if I want to do a level C Linux, I have to do full structural coverage on at least, we're guessing, about 1 million lines of code. So that's huge. So I'm always curious if, like, ASIL B, it's like that doing it with Linux is interesting because when I relate it, to like the failure rate, it's definitely ASIL B within a context of a scenario. And I'd be curious, that'd be a really good debate with someone that has that knowledge and more on the ASIL side at some point for sure.
I have one
Oop,
point.
sure.
I was wondering, and I'd like to hear the audience feedback, because from a lot of things which happen in automotive, I often see that we either cluster in A and B and C and D, because the tools and rigor which you have to apply
Yeah.
are more or less exactly the same for A and B and C and D. So I would have assumed that we maybe say that C and D is a dull B, and A and B is maybe a C thing.
It's more like a DAL D. A and B, from what I've seen, there's no way it's covering the things that C's doing, but they're two different life cycle processes, right? So they're trying to achieve slightly different things in different ways. So, I
say maybe more the ASIL A and B is the dull D thing, and then ASIL C is dull C, and ASIL D is dull B.
a little bit, yeah. And the one interesting thing right now is I'm working with Zen on their ASIL D, and we're going to try to see if we can get DAL A artifact work done when they do their ASIL D, such that we almost elevate Zen beyond an ASIL D as a first go, which means like some intense like fault isolation stuff, a lot of low-level requirements and other things like that really did fill this gap right here, as an example. So, couple other domains to mention, the level of rigor and the NASA class. These two are both addressing a space, I'd say, that's sort of between aviation and more general safety. Because if you think about like your human life factor, it's definitely a little different for LOR and class. And I encourage, if you're curious about that, the standards are linked there. Our team is looking at, I think, more the class. So comparing aviation versus NASA class comes up in our group. So time check. All right. So use cases. So this is what the Aerospace Working Group has been working on for a little over a year now. And the rough process here at the top that we're following is proposing, trying to capture and write them up. And in a lot of cases, we get at least through step one. And then we try to drum up support and start writing it up in step two, and progress all the way to creating a demo and then publishing it. So either in a forum like this, or Martin was suggesting yesterday, maybe if people are interested in writing papers on that, that would also be an avenue. And the table here takes our use cases and maps them to those different levels and severity perspectives. So far, everything that's in the first three levels, which I lumped together because it's a different class of product when you're in those levels. And if you're assuming a level C, honestly, you may as well assume an A and work through your scenario and what you're demoing. So cases that came up had goals around mixing the different levels or mixed criticality, looking at minimal code base and the configuration approach, fault trees, IO, voting schemes. IO and protocols is really interesting because anything A through C, you really have to assume you don't have a stack. So no network stack, no graphics stack. You got to think outside the box and how you're going to approach it. And it's mostly, you go back to that, my code base has to be minimal. And it's an extreme energy and cost investment to do A through C level of life cycle work. So in the cases, I think we had a little bit of traction in the last few weeks on doing like an emergency lighting example. So it would take our cabin light demo, which I'll show in a minute here, that's fairly mature, and go retarget it to what about emergency lighting? What would the scenario look like? How would I implement that? What would the back-end environment OS and technologies be that I'd use? So that might be what we're talking about in our December aerospace call. But moving to level D, this is where we've been focused. We've been trying to get a first use case example demoed. We had great help from Paul Monty at Collins Aerospace, did some of the test writing. Yvonne at NASA helped us integrate co-pilot monitoring approach, and myself, Brian Wood, Salim at Boeing have been doing some of the environment container work and a little bit of the CFS work that I'll show. And then Martin Hall, my co-lead, has been working with us on going through the use case development side, but then also we're starting to translate it to usability and the goals of what we're trying to assemble. And he's been working through sort of that basic workflow and environment side of it as things mature. So yeah, shout out. It's been great to get everyone together every week and work on this for the last year. It's one of my better meetings of every Friday. So so I'll show that green in a minute, and then I'll show the yellow one, this example where we took NASA core flight system and are trying to rebuild the demo on top of the flight system as a concept. And then level E, we had an idea come up related to a tested boot, which doing some integrity authenticity stuff. And with any of these, if you have interest in them, that QR code will get you to our discussions page where you could actually go vote on these. So I think I have an example here of, yeah, you can actually go here and just click the button to vote up if you're interested in this use case for fault tolerant. Or if you have a new one, just create a new discussion, prefix it with use case, tell us a little bit about it. We'll talk about it in the next call that you're invited to, and we'll see if we can mature it towards a reference example. So first demo. So a little over a year ago, we started capturing the initial requirements for this very basic case that you could equate to toggling an LED, which toggling an LED most likely has a constraint of timing to turn it on and a timing of turning it off. And then when you go to design it, you're going to say, well, there's really maybe three components: a switch, a server that does it, and then the light itself. And when we looked at verifying this, that's where Yvonne brought up co-pilot monitoring. So it's not the co-pilot like code assistant, but the co-pilot framework from NASA to actually monitor that your original conditions that these requirements are saying. So you basically write a logic agreement and then in Haskell, and then it basically builds the monitor to perform that continuous monitoring behavior. So I'll show that when I show this in a minute. And that test monitor sits here in the diagram out on the side, and it monitors log data, Ethernet traffic data to verify it's running as intended. So your progression there in the diagram is I'll show the switch app talks to the light app, talks to the light with some Ethernet flows, and then logging of some events. So, and we actually built this native, and then we built it emulated. So I'm going to show native, but I can show you what our CI is doing that shows the automated. Get to the page. So if you want to recreate what I'm going to show, you can go out to our aerospace working group repo out on GitHub, demos, README, and in the README, we basically have our rough manifesto for what we're doing for demonstrations and goals. And then you'll see the light switch, and then the basic demo. My environment's already set up, so I'll skip to this one for now, but we spent a lot of time making sure this is reproducible across a bunch of people's corporate environments, personal environments, and everything is fully isolated in a container, including the emulation sides of it. So if I look at the demo, here, if anyone wants to poke at this while I'm presenting, I'll drop it in the chat, maybe. You grab our repo, go to our example monitor project, grab your initial environment, generate the code, build the apps, and then what I'll pull up here in a minute is I'm going to do a make run, which is going to create a Tmux view of the different actors in the system. So you're going to have a monitoring app, a light app, a switch, and yeah, so I'll see that here quick. And like I mentioned, this is also available for emulated. Everything is set up as make targets. So the make file in this monitors folder sort of abstracts your environment setup, your ability to do like a native example or an emulated. And it'll go pull like our emulated content that I'll show after this. So you don't have to like build an OS or anything like that. And so, all right, so in the upper right here, this is the Copilot monitor. So this is running and it's monitoring logging. This is your syslog output from the server and from the switch. In the upper right, this is the server. So this is the thing going, oh, you told me to switch, and it goes and it switches the light. And then the bottom right is the actual switch app. So right now it's not running. So I'll start the switch app. So on the left there, you see it's saying it's sending messages. It's switching itself on and off. Behind the scenes of all this, we're using a little bit of networking. We're using some logging. It's definitely level D as in Delta components of the kernel. When we move up to level A through C, we would reevaluate, do we use raw frames? Do we not use Ethernet? And some of that will flush out in like a critical, emergency lighting scenario would change your backend Linux dependencies and how you describe the system. So here, there's rules in play here that monitor's watching for. So if I invalidate the requirement on delay and say, bump the delay up by a millisecond, you see we just got a monitor violation on the lighting behavior didn't occur. So that is the console demo. But a lot of stuff went together with this. And what it provided is that we can now rehost this in different environments with different dependencies, and there's a test framework around it. So, yeah.
One question, can you hear me? So the code which you're executing is running on the Linux in a Xen hypervisor environment, or what is?
So what I was just running on Linux. It's not running on a hypervisor. We have it running in like an emulated OS. So I can actually.
And is this a real-time kernel, because you're testing some time-related features? So
it does have RT enabled, but we're not scheduling it as RT right now. But those exact things would be very good constraints that we could put on the like a level C example, taking the same concept, adjusting those parameters to be requirements, and then redeploying. I do want to show in our automation, this is an example where we actually boot our minimal Linux, and all it does is basically run the same monitor sequence that I showed manually. This is running an ARM emulation. So this is booting a kernel that's like about 500,000 lines of code. And you could start chipping that away towards a level C example with those constraints that you described. So you would run this as a Zen partition. And so the other thing we're showing is this example here that booted to do this. We have projects out here on ELISA Tech's GitLab side, where we have this demo cert Linux. And it's super basic build. So it just goes and basically bootstraps a kernel with a minimal config, and that's it. There's nothing else in the system. And then we archive it, and when you do that make step, it actually goes, pulls the pre-built, runs the pre-built, puts your application in, and then runs our use case. So if anyone wants this as a topic, like in our December aerospace call, I'm happy to dive into it there too. And we can go in way more detail.
When you're talking about DAL C implementation, I think the problem is a little bit if you run with additional software on the same hardware, as the segregation in time between these.
Yep.
And especially on multi-core, I think it will be very complex to show that there is no interference.
Yeah. So working towards exactly that scenario, this mixed criticality case is actually one that I put on the list because doing full, robust time and space partitioning with the proofs that you described and the fault approach and everything planned out is something that the Zen community is doing with an automotive slant, but we could very much bring the aviation scenarios along the way as they're doing their ASIL-D work. So I don't think that one's impossible. The thing that becomes a little more interesting is, what do you use as a partition runtime for things that are above a level D? And there's been a lot of ideas in that space, and I think we should definitely debate on if it's Linux or not, right? Or if it's a progression towards Linux, because you're going to have to hit a partition runtime that hopefully is like around 50 to 80K, which would not be a lot of Linux left. That would be more like looking at a really basic like HAL on top of a bare metal or something. Closer to what you'd see in like an ARINC 653 OS. So,
so the idea is that in the Xen hypervisor, you make the segregation, and then you have only, let's say, a very poor partition where you not really Linux is running. You have a very limited implementation where you can show coverage and everything. And also, you think that you can certify the Xen hypervisor. The lines of code are not too much. You see that there is a chance.
Yeah. So the cert profile on it is about 50 to 80K, depending on what's in. And with the ASIL-D effort right now, there's been discussion on actually having the design material represented partially by LLRs. So we would already have some of the LLR input material to start reverse engineering on that, maybe 80K worth of content. So it's a lot more practical than running Linux, since you already have 653 scheduling in place. So like you have that broad partition scheduling and all of those strict bounding enforcements, get all that proved to level A, then the partition side becomes more of a, what's the first step, and then what do we aim towards? I think those will be great ones to try to capture and mature here in this category going forward. Collins Aerospace is also interested in mixed criticality architecture and trying to do a reference. That came up in a prior call. So other example real quick, I was going to try, we can come back to some of this too. I think we'll have a little bit of time. Go ahead.
I have a question regarding to your comparison.
So I liked it really much to see the different ASILs and SILs and ASIL matching. But you didn't touch base on the certification. So in ISO 262, the word certification does not appear at all. And somehow certification is something voluntary. However, when you want to bring a car to the street, at the end you have the type approval, who is then rigorously checking, not only the ISO 262 but other laws. So what's your take on this? So is it a big loss or is it an advantage, or what would you comment on the difference? Because to my knowledge, the certification is written a part of the DO standards.
Yeah, it definitely, you have certifying authorities, and there are some that have delegated authority to certify, which is definitely a privilege, and not a lot of companies have that. But going through that, I think the thing that has to be considered is whenever you're taking something for reuse, I wouldn't use the word reuse. You may have material that you can consider and put together and maybe try to establish a prior baseline that you're building on, but you realistically have to go back through the full hazard assessment process, get your allocation of safety requirements, and then do your system and your planning activities and your life cycle activities. So it's a much different perspective of like if a vendor can't just go certify, say, an operating system to 178 level A, they have to be in a product that's certified to A to make that claim. And then if for reuse of it, it's more, I've done it before, I'm bringing some materials, but you still got to go through it again. So it's a little bit different. Yeah, I don't know. A lot more regulated.
Okay, thank you.
Yeah, I do see gaps in ASIL that there are areas that are subjective on what's enough rigor. And I'm not knowledgeable enough to comment more than that, but it seems like there's areas where there's definitely not the same amount of activities as you would see in a 178 like failure rate equivalent. But it might be the way you're achieving it too, right? So
there's one point when you look to the tools. So in the ISO standard, in the IEC standard, the tools are considered less critical since they are part of the product. And in the DO standards, the tools are have the same rigor as the software. So when you want to qualify a tool for A, you have to achieve MCDC code coverage within the tool according to the DO 330 standard, which is I'm not sure if this is still considered as valuable or good, or what is the rationale behind it?
That is actually one area that's really interesting, where I think there's a lot of goodness that can happen in the open, is if we get to a baseline of tools that have DO 330 verification material and plans that are public, such that there's less of a corner on the market of those. And the reason why is because they're all related to quality. If that stuff was more readily available, and a sad pitch for Boeing investing in coverage tools, if that stuff was more open, code quality would go up generally. You'd be able to understand your coverage and maybe apply energy to areas that do have solid impact. So like your cyber aspects of things could improve. So I think there's a side effect to having the 330 stuff public, as well as that activity is costly. And if everyone was doing DO 330 on, say, your GCC or your LLVM, that is a lot of industry waste, right? That raises everyone's cost. So that is definitely an area that I think we can chip away at.
If you look to the code coverage tools from LLVM and Klang, they are part of verification. Therefore, it's TQL5, and you can qualify them. TQL5 is like ISO 262 qualification. So we have done this. We come up with that. But when it comes to the compilers, the Klang and GCC compiler, they are TQL1, And this means you have to test them until you have achieved MC/DC coverage, which typically is there are workarounds for people not doing it, and they're ending up in testing the object code level at the end.
Yep.
But this is, I think it's a bit of pity, because if they would have tool confidence like we have in ISO, which a bit less rigor, then it would be possible to qualify these compilers for avionics as well, and then they would not need to do all the object code coverage.
I saw
all safety standards, IEC 61508, they do not require the tools to have the same criticality. So maybe this was one step too far from the DO standardization.
Well, I'm guessing their root cause analysis and escapes are definitely going to drive behaviors and standards. So there's probably a historical reason tied back to an era when something wasn't as reliable, or some event couldn't be bound without writing it in. So I'm a little curious to see where topics go as AI and AI tools come to play. And those, I'm not up to date on the regulation standards being worked in that space, but it'll be interesting to see where that falls versus the other tool qual. So yeah. The last demo here, quick, one that we're still maturing. These demos are all volunteer. So we broke this one down because there's a number of parts to it, and we're right now on, I'm going to show item number 1, which is demo a basic CFS app. So what this does is it establishes the core flight system, which has a software bus and basically this message passing approach. So you'll see the basic boxes from the last demo, but the IPC in the middle is changed. And what's interesting here is I can realistically remove the network stack in this demo, because this is pure basic software bus, basic communication. So you could think of like a satellite in space. The radio may be a serial interface. So this demo could get a message from the ground that would appear like it came through a TTY device that hits the software bus, then it's propagated via CFS into the app. So I'll show that. We are going to improve the demo beyond the basics and basically add the monitoring, and then do the basic thing we did with the lights before, with the lights app being a quote ground system, so that it's, you're signaling that. You could think of it as maybe not lights, but you're just signaling defrost or something, from the ground on a satellite, and then the satellite's taking action. This demo becomes a little more interesting for these items here at the bottom. It is using a minimal Linux with CFS cross-compiled for it. And I'll show you the pattern was documented of how to do that. So this is super minimal, no library dependencies, just standard library and the kernel. It's using a tool called Augma, which allows generation of monitors. It applies to CFS, F prime, space ROS scenarios, but it's a way to take a definition and then have it do autocode generation. And if you have more interest on really driving into Augma, it's all out on NASA's page. And from there, you can get to like what CFS is, Robot and F prime. So the links are all there. So demo wise, jump to first with this progression here. So building CFS document is out in our demos docs. This one is not wrapped up nicely behind a make target. It is still very much you drop to a dev shell, which puts you into our container, and then you go through a progression of grabbing CFS, patching it so that the demo app build it, compose a file system with the sample app that runs with CFS. And an important thing here is that CFS really can't be built and deployed separately. So you couldn't build like a CFS daemon or a CFS library easily that you could then just deploy and then install apps against it. Right now, the ecosystem and how I understand it is you're sort of building with CFS, and that's what you deploy. So that paradigm's a little different. So we build it here, and then we also add basically this command util that allows us to simulate the ground to poke at it. So I will show you this run example here, but docs are all out there if someone wanted to go through this sequence. So this will be wrapped up behind a make file is how we've been doing them so far. So it'll be much simpler to run the basic demo once it's complete. So I've gone through all that setup, which takes probably about 20 minutes or so. And I've got a file system packaged up, a CPIO with the CFS added to it, and a minimal kernel. So I'll boot that quick. And I'm not on a super fast system. I think this thing takes, the kernel is so stripped down, it takes about 200 milliseconds to boot. So, the config for this is public. So if you are curious about that, it's out on GitHub, and happy to share that. All right, so I booted it. I'm now inside the emulation. So I'm going to go to where we copied the CFS stuff, and then behind the scenes, I just ran CFS. So the framework's running. And then here, let's grab my last command, the ground system command. So here in the log, when CFS started, you can see it initialized the sample app. It plugged it into the bus so that it can get messages, and it's just sitting there listening. So if you read a little bit about the CFS system, it's basically a way to have reusable apps across missions, and it provides a little bit of like a hardware abstraction on top of the OS. So there's some portability, and so I think they have a HAL and a PAL layers in how they support app integration. All right, so here, this is going to simulate as if I was a ground system sending a no-op via packet ID 1882 to that sample app up in the satellite vehicle. So it sent the data, and then here, that data went across the software bus and went to the sample app, and it got the NOP. So super simple. What's neat is this wraps up a practical concept of building an embedded system that you could target to real hardware with the CFS framework, building an app with CFS, and then moving a little bit of data around so you sort of get an idea of, well, how do I define a message, how do I decode a message? So it takes the example that CFS had just a little step further. So that's it for that one. And if you're curious about anything from this talk today, or just want to join our one of our specific calls, the first one is general topics where we do use case work, presentations on things. Third Thursday is when Space Grade Linux meets. They are sort of in a distro road mapping mode. It's really interesting if space is your targeted product. And then Thursday, we have industry paper session, which Martin presented on yesterday. If you're interested, his video walks through possible topics. This last one is definitely a working session for that. And then weekly, a group of us meet to work use cases. So this is where we advance things to reference concepts, improve ones that we've started. And that's how we got these demos. So mailing list here if you're curious. And if you need the invites, that QR code will land you on this meeting page. And the Aerospace Working Group is one invite to register for. Space Grade Linux is another. And then the use case testing call on Fridays. So there's 3 different meetings that you'd have to sign up for depending on your interest. So that's all I got. Any questions?
No question currently
Cool.
from the audience here. I don't know if something is in the chat. Check it.
No.
No.
Well, I guess if anyone has interest in helping us write use cases, even if they're like, I think cross-industry ones would be interesting, just to learn about like what would a combined level A ASIL D solution look like that maybe provides foundational technology for something that could be interesting. If Zen functional safety is of interest to you, there is a call every other week with AMD in the Zen community. That's another one that a few of our members are tracking because it ties directly into these scenarios and things that we're assembling for reference. So
Matt, I have a question regarding tool confidence and tool qualification. This is a bit different in the DO standard than in the other standards. So you have a plan of safety aspects for certification that contains something and other things, so which are not fitting to the current model in the SPDX and in the things so far. Is this something you discuss in your group? So I would be interested to do so, but I don't want to be putting things into your group that are not interested in.
I think it would be interesting. It's an area that hasn't been touched on in the ELISA group. In the Zen group, it has, because defining that plan for certification really ties together the tool use, your partitioning plan, and some of these things that sort of all tie to, well, what's your reference architecture deployment look like, which is what you need to do fault analysis and other activities. So
which meeting would you recommend to join then?
I would join the aerospace working group call, which would be the one that meets. The invite would be on the 2nd Thursday of the month.
Okay.
So
can you send this to me or invite me there?
yeah, let me grab.
I just sent you a LinkedIn connection request. It's Oscar Sotosh.
Cool, that's perfect. Yeah, no, I can send you a link.
Cool. Thanks.
Yeah, no problem.
Cool. And this brings us to the more or less last part of the day, which is called Day 2 Wrap Up. There's no slide there. I think Bertie could stop the recording, right?
We can.
Yeah, no need to have it. Just